I'm going to start recording as well, so if anybody has to drop off, you can access the recording of the webinar at a later date. We will post it as soon as it's compiled. So thank you all, and welcome to today's installment of our ongoing series of informal but informative webinars hosted by Men&Mice, covering topics of interest regarding changes and new developments in the enterprise networking space in general, and those areas impacting the DNS space in particular. Since 1990, the Men&Mice suite of DNS, DHCP, and IP address management solutions has been the solution of choice for enterprises, large and small, as well as governmental organizations like the U.S. Department of Agriculture, the Department of Commerce, and components of the DoD I won't mention because, well, they don't officially exist. In partnership with ISC, Men&Mice is also the leading provider of DNS, DNSSEC, and IPv6 training courses worldwide. Today, we'll be discussing what those party animals over at the Internet Engineering Task Force have been up to at the recently concluded conference in London. Men&Mice's own Carsten Strotmann was there in person, and he'll be bringing us all up to speed on the various issues that were raised, including internet privacy and security, that affect us all. Before I hand it over to Carsten, I'd like to introduce myself. My name is Paul Terrell. I am one of the regional directors with Men&Mice, and I would like to remind everyone that there will be a Q&A session after the presentation. I'll be collecting questions throughout today's presentation and submitting them to Carsten at the end, so please don't hesitate to use the Ask Question functionality built into the meeting client. And if you have any questions about functionality, feel free to ask those as well, and I'll help you out during. So without any further ado, live from the Men&Mice Professional Services team, I'd like to introduce Mr. Carsten Strotmann. So Carsten, take it away.
Thank you, Paul. Hello, everybody. Welcome to our IETF 89 review today. Now, this is the first time we do this IETF review. We have done that previously only internally to the Men&Mice stuff, but we thought it might be of interest for you as well. So we know offering. We would really be interested about your feedback on the format and whether you like the format or if you would like to have changes. You can either give us feedback after the presentation in the question and answer section or send it by email. So what is this all about? The Internet Engineering Task Force is a group of people, network engineers, operators, and other people that come together and work on Internet standards. They write the standards document, which are known as RFCs, request for comments. And the work on the IETF is mostly being done on mailing lists, but once in a while, people working in the IETF meet, and there was such a meeting in London last week. And I would like to give you an overview what has been discussed there, mainly on the future of the Internet, so about new protocols and challenges the Internet is facing today. The IETF meetings are really, really large. There are, I think, almost 1,000 people or even more than 1,000 people there, and there is a large number of working groups. Working groups like voice over IP telephony and security in web protocols. But for this webinar, I would like to focus on just DNS, DNSSEC, and DANE. We'll give you an introduction what DANE is a little bit later. DHCP and IPv6, because that is these are the topics that Men&Mice is involved in. However, this is just a selection of what's going on, even from these working groups, from these topics, because it's impossible to just find everything and present everything here. I hope I found a selection that is of interest for you. So let's start with DNS and with an overview of all the RFCs that has been published since the last IETF meeting, which was in November last year. And in the DNS space, from the DNS working groups, we have 4 RFCs that I picked that I find of interest. The first one is about architectural consideration of applications in DNS, and that is a document that explains what developers that develop new applications that make use of DNS, like storing extra application-specific data in DNS, should consider when they design the application and the protocols. The next one, about resource records for EUI 48 and EUI 64 addresses in DNS, is something that has been implemented on specifically for people in Canada, because in Canada, ISPs and service providers have to publish the link layer addresses, the MAC addresses of certain consumer gateway devices like DSL routers or cable modems in DNS, in a private DNS that's not going into the public DNS. And the RFC specifies 2 new resource records which can be used to store Ethernet or other link layer MAC addresses in DNS. Now, this can also be useful for other users, for example, to build an IP address management functionality on top of DNS in an internal network. However, as the RFC points out, it is a privacy problem if these addresses, these resource records, the link layer address, been published in a public DNS. So they should never appear in the internet. It makes sense to have that in an internal closed DNS. The third one, RFC 7050, is about a way to use DNS to discover the IPv6 prefix used in IPv6 address synthesis. That means in technologies like NAT64 and DNS64, a special IPv6 prefix is being used to translate IPv4 addresses into IPv6 addresses. And this translation is usually be done inside a DNS server. However, sometimes applications either get the information directly as literal IPv4 addresses that need then to be translated directly in the application, or a client might decide not to use a local DNS server, instead use a DNS server of its own choice, and then that DNS server cannot do the translation. And this RFC describes a way how to find out this prefix. And the last one is an informal RFC that goes into detail how the authenticated denial of existence in DNS and DNSSEC works. With authenticated denial of existence is meant how DNSSEC can prove that stuff doesn't exist. So how negative answers from DNS are being secured. It goes into the detail how the NSEC and the NSEC3 resource records work and what options zone administrators have when they sign the zone with DNSSEC, and how they can secure these negative answers. So this is like already published work, and now we come to what has been discussed last week in the IETF. There was a new BOF session, BOF standing for Birds of a Feather. That is, people of equal interest meet and discuss about one certain topic. And one big topic in last week's IETF was encryption and privacy in DNS. And the DNSE stands for DNS encryption, was not a working group, was a gathering of people interested in the question, what can we do to make privacy in DNS better than it is today? DNS traffic today is unencrypted, so it reveals a lot of information about the user, both on the wire for someone that can just listen on the wire, seeing the traffic going between a client and a caching server, or between a caching server and an authoritative server, and also a lot of data can be collected on the DNS service itself. Since the revelation last year from Edward Snowden, the IETF has a plan to harden all the internet protocols against pervasive monitoring. And DNS is no exception here. So during that meeting, several proposals have been presented, as well as a problem statement that explains what's wrong, what is the danger of the current unencrypted plain text DNS that we have. Among the solutions that have been presented were a DTLS, which is an already existing RFC to make TLS, which is transport layer security that we know from the web browsers as SSL, to use that over UDP traffic. And DNS being UDP traffic, DTLS could be used to secure and encrypt traffic between DNS clients and servers. Another technology is DNS Crypt and DNS Curve that have been deployed in some installations in the internet already. Others are GCA TSIC that works on cryptographic generated IPv6 addresses and is using the already established TSIC transaction signature protocol to communicate securely between two nodes that exchange DNS messages. Confidential DNS is a lightweight way to exchange cryptographic keys between two DNS clients and or DNS servers. That one is from NLNet Labs, the people who do the unbound caching server, and NSD, the authoritative server. And the last one is TDNS, which is a proposal to use Start TLS for TCP DNS. That is not using transport layer security over UDP like DTLS is using, but instead focusing on using TCP and forcing all secure DNS on a TCP connection. The meeting had no conclusion, so there were no direct action items here, but it is been apparent that this is a very important topic, and the discussion will continue on the mailing list, and we will probably see possible solutions later this year or the beginning of next year. Then in the DNS Op stands for DNS Operations working group. There were two documents that had been written a long time ago and then fell dormant. They have been revived in this meeting last week. The first one is a document that documents how DNS resolver, that is caching name servers, prime the root zone. You might know, if you are working in the DNS space, that every caching name server has a root hint file. That is true for bind, that is true for unbound, as well as for the Microsoft DNS server. The root hint file lists all the names and IP addresses of the root name servers. However, this file can get out of date. So when starting up, a caching name server needs to make sure that it has the last recent version of the IP addresses and the names of the root name server, and it usually does that by sending a query to one of the root name servers. DNS servers have done that for a long time, but it has never been documented how this is properly done. And this document now sets out to formalize that procedure and documenting how resolver priming should be done. And the second document that has been revived is the DNSSEC Key Timing Considerations, which explains the relationship between all the parameters used in a DNSSEC key rollover, meaning the lifetimes of the signatures, the time to lives of the various resource records involved in a key rollover, like the time to lives on the key material, on the delegation signer records, and so on. And this is important information for both people who implement DNSSEC key rollover automation software, either a script or commercial or open source tools, and as well for DNS administrators that plan to use or to do a manual DNSSEC key rollover. These people need to know how the timing is to be calculated, because doing the timing wrong and especially changing certain resource records too early can have fatal consequences on the availability of a DNSSEC signed zone. Another topic discussed was about special use domain names. Since last year, since RFC 6761, there is a special use domain name registry inside the IANA, and there's currently one domain name being set aside as a special name. Now, a special use domain name means a domain name that is not used in the internet. It's not delegated, it's used for some protocol, and name resolution happens in a different way. It's not happening through the normal DNS, so not using iterative name resolution, looking at the root name server and following all the delegations. Instead, that name resolution is done in a different way. And the one name that is currently in that registry is the .local domain, which is used for multicast DNS and local service discovery. And it's most popular in Apple operating systems, where it's called Bonjour, and it's been used there for sharing of music through iTunes or photos from iPhoto and similar applications. Now, there are already other software systems that use name resolution outside DNS, and these are mostly in the privacy network space. Examples are the Onion Router Tor network, GNU-Net, which is a new encrypted overlay network that is built by the GNU project to basically create an encrypted overlay network that lies on top of the existing internet infrastructure. I2P is a similar but different approach of creating an overlay encrypted network. And there's Namecoin, which applies the ideas of Bitcoin to name resolution. So all this already existing and deployed software is using their own kind of domain names with their own top-level domains like .gnu, .onion, .exit, .bit, and so on. You see them on the slides. And there's a proposal to register all these names now in the special use registry to prevent that someone else is using them. For example, as you might have heard, we have quite a lot of new top-level domains since recently. And it could be that someone tries to register the top-level domain .onion, like the Association of French Onion Growers or something like that. And to prevent name clashes, these names should be blocked and not be permitted as regular top-level domains. And all that discussion on the special names triggered another proposal, the proposal of having a .alt top-level domain, which would be set aside for all the special names to prevent too many of these special name top-level domains. The benefit of having just one single .alt for alternate top-level domain or any other name, but just one being set aside, would be that that top-level domain could be blacklisted in DNS caching servers, preventing the leakage of the special names out into the normal internet systems. What we see today is that a lot of these special names, which are meant to resolve names in their special networks, sometimes leak out and being seen on the root name servers. Now, this is not good for the root name server system, and it's also not good for privacy, because these special names are often used for privacy software, and if lookups for these privacy software names are being seen at the root name server system, they are not really private anymore, certifying the use of privacy there. Another proposal that is a rather old one is about DNS cookies. And the idea of DNS cookies is to have some random data like an identifier key exchanged between a caching server and an authoritative server, or between a client and a caching server, whereby both parties that are in the DNS communication can kind of know each other, and if then there is a request or an answer coming from supposedly the same IP address, but not having the same random information, is being detected as a cache poisoning or answer forgery attack. There's a proposal on how to implement these cookies using the EDNS0 OPT record. And this is how it works. Now here we see DNS cookies being used between the caching server and the authoritative server. We have a caching server in the middle and a client on the right-hand side that is sending a request for example.com, a record, to the caching server. The caching server is forwarding or is resolving that towards the authoritative server. And here, the caching server is adding his own cookie inside the OPT resource record in the question. The authoritative server stores the resolver cookie together with the IP address of the resolver, and it sends back the answer, and in the answer it contains its own cookie, which is the server cookie, the authoritative server cookie, and the caching server then stores the authoritative server cookie in his own cache. Now there is a relationship between the authoritative server and the caching server with the secret information, the random key that has been exchanged through the cookies. Now the client gets the answer, and when at any later time the attacker sends wrong information with a spoofed source address towards the caching server, the caching server can detect that this data is not really coming from the authoritative server on the upper left side, but it's coming from an attacker, because the attacker cannot know the value of the cookie and can therefore not send the same cookie as the authoritative server would do. So this is a lightweight approach. It does not stop all kinds of attacks, but it can limit a number of attacks. Cache poisoning attacks, forged data sending attacks, and some kind of denial of service attacks. A prototype of DNS cookies has been implemented in bind 9.10. The implementation in bind 9.10 is not identical to the IETF draft, but it's quite similar. And the beta 1 version of bind 9.10 is now available from ISC. And let's see, I'm not sure if I have, no, I don't have an example here, but you can try it out if you set up in a lab environment two bind 9.10 servers. You can then see these two servers exchanging the cookies. Because the cookies are in the EDNS0 OPT option, any server that doesn't support DNS cookies will just ignore that data and will not act on that. Because currently there's no RFC standard, these cookies use an experimental OPT option code. And once the proposal will be accepted by the IETF and will become an RFC, there will be a standardized option code being given for that. On the client side, DNS today is much more complicated than in the 1980s when DNS was designed. Today we have DNSSEC, we have DANE, which we will cover a little bit later. We have new record types, we have SRV records that it's handling, and the libraries that applications can use in Unix and also on Windows have not been involved in the same speed as new functions have been implemented in DNS. For example, today, applications that want to make use of DNSSEC would need to implement DNSSEC validation on their own. And it doesn't make sense if all applications do that. Instead, that should be a function in a single centralized operating system service or in a toolkit. And the NetLabs, VeriSign, and No Mountain Software have come together and produced an open source client resolver library under an open source BSD license called Get DNS API, based on an original specification from Paul Hoffman from the Virtual Privacy Network Council. Hope I have that correct. And that Get DNS API has support for DNSSEC validation. It can make use of checking SSL certificates through DNSSEC, and it knows all the new record types, and it includes SRV record handling, and that should enable application developers to make use of all the new functions in DNS without writing all the stuff themselves. That new API is available today on Red Hat and CentOS and on macOS. It's in the Homebrew package manager. So if you have Homebrew, you can install Get DNS API today. However, because it has just been released last week, there are not many applications today that make use of it. But if you are an application developer, you might want to have a look on that. Soon, Get DNS API will be available on FreeBSD, and we think that the other BSD operating systems will follow soon. There's already a port to the Apple iOS operating system running on iPhones and iPads. It's currently a little bit rough but usable, and there are already people using that API on iOS to implement that into their applications. And work on Windows and Android ports is underway. And for people who don't like to code in C programming language, there are language bindings for Python, for Objective-C, for Java and JavaScript, and there's probably more to come, Ruby and other programming languages, Perl, and so on. And that was the DNS part, but we stay with DNS and have a look on DANE. They have no DANE-related RFC being published since the last IETF, so that's easy. But what is DANE about? DANE is a protocol or a suite of protocols that use DNSSEC to provide opportunistic encryption. That means encryption without the need of manual configuration, either with or without certification authorities. That basically means that it works very similar like the SSL TLS that we know from the browser space, but it gets the certificate information from DNS instead of using the centralized certification authorities. There's much interest in the DANE work from the IETF. The working group room was packed. People were standing in the aisles. And so we will probably see a lot of adoption on DANE in applications in the next time. What we already have available and what works is DANE in web browsers. There are plugins available for Firefox, Opera, Chrome, and the Internet Explorer from DNSSEC Validator CZ. And what these plugins do is, if you surf on a website that is SSL encrypted, so you have the HTTPS protocol in front of the URL, it will validate the certificate presented by the server through DNS. There is either the whole certificate or a hash of the certificate being stored in DNS, and the plugin can check that and make sure that the certificate is correct. That prevents from any screw up on the certification authority side. So if a certification authority is being hacked and some hacker is able to create false certificates for your website, still the DANE plugin would detect this because the new certificate would not match the data being stored in the DNS. New work is being done on the email side. today there is transport layer security available for email for SMTP delivery, but it has many, many issues. For example, certification validation is not mandatory and often not possible. So encryption can be done, but nobody can be sure that the mail server is really talking to the correct other mail server on the other side. And the plain text communication is the default, and encryption is just optional, meaning that a man-in-the-middle attacker can always force one of the two parties to downgrade, that is, send all the data in plain text instead of using encryption. Now, DANE works in a way to specify that a TLS connection is mandatory between servers. And that works in a way that the sending mail server is looking up first the MX record for a certain domain. You see the DNS lookup for an MX record in the slide. So here, like we want to send email to the domain titlelock.de, and the mail server for that domain is ns3.titlelock.de. And then in a second step, we ask for the TLSA record, which holds the certificate hash for that server on a name, on a domain name that is the name of the server itself, so ns3.titlelock.de, and in front of it we have the transport protocol _TCP and the port number for the protocol here _25 for email SMTP prepended to it. The answer is what we see below, which would be the hash of the certificate that we would expect on the remote server. And now our server can make a secure connection, an encrypted connection to the remote server, and can validate that the certificate presented on the remote side is exactly the certificate that is being stored in DNS. And if there's a downgrade attack and the machine on the other side pretends to not be able to speak encrypted email, then the sending server can just stop communicating, because the data in DNS mandates that the remote server can do secure encryption. This has now been implemented in the postfix mail server, version number 2.11. Which has been released in February this year. And Victor Duchovny from the postfix team presented at the IETF about the challenging of implementing these TLSA checking in applications. And he found that implementing it right in software is quite complicated, and it's easy to get wrong, and that there needs to be a toolkit. Happily, Get DNS API that I have shown you before might be just this toolkit. And there was also quite interesting presentation on the postfix TLSA implementation during the free and open source developers meeting FOSDEM in Brussels in 1st of February. We will have links to the other non-IETF and also on the IETF documents in our webinar page on the Men&Mice website later on, where you can also find the slides. More work on DANE. There is a proposal for using DANE for voice over IP for SIP. That is for Internet Standard Voice over IP. And that would enable telephones to validate or to fetch certificates to encrypt voice calls with central gateways or with other phones. And there is now also DANE for SRV records, which can be used, for example, for the Java instant messaging protocol. And I've just looked today, and even today we have already 58 Java servers that are using DANE and DNSSEC to secure their communication. And it's getting more and more. Given that that protocol is just in development, it's not specified, it's just a draft. That's amazing that already so much code is out there and so much software is supporting it. Another interesting development in the DANE working group is to store PGP keys in DNS. Today, PGP, which is pretty good privacy, a way to do end-to-end encryption in email, is stored on central key servers, just as pgp.mit.edu. And there is a proposal to store the PGP keys not on these key servers, but in addition to that, store them in the DNS. And here's how it works. The PGP key information is stored at the name of the user part of the email address, not the whole email address, just the user part, that is the left-hand side before the @ sign. That name is being hashed with the SHA-224 hashing algorithm. That is required because a user part of an email address can contain characters that are illegal as domain names. And we see here the SHA-224 hash of the name Paul. That is for Paul Wouters, who worked on the draft, and his email address is paul@noheads.ca. And if we have the hash, we can then make a lookup for an open PGP key at the hash name _open PGP key and then the domain name. And we see here that request returns the full PGP key encoded in base 64, and an application can make use of this and automatically fetch the keys, encrypt the email on the fly during sending, and then the recipient will get an encrypted email for his own keys. And there's already code that makes use of it. There is a Milter plugin. A Milter is a plugin for a mail server, and the plugin works for both postfix and sendmail. And what it does is, if email is being sent out through the mail server, it automatically fetches the PGP key, if available from DNS, encrypts the email, and sends it on. So the user does not need to know about encryption at all. In this case, it works just automatically. The user can use any email client, just send it out to the local mail server, and the local mail server makes sure that the email is encrypted. If you want to create your own open PGP key record in DNS, there is a tool called HashSlinger, which is available from GitHub and also available already on Fedora Linux, where you can install it, and that has an open PGP key command that you give your email address, and it will automatically create the DNS resource record for you, which you then can store in your DNS. And last but not least, it's IPSec in DNS. And there's an idea to store the public IPSec keys in DNS. So if one host that supports IPSec, and because IPSec is a mandatory part of IPv6. A lot of IPv6 capable operating systems do IPSec. So such an operating system can then just look up the IPSec credentials from a remote host, create an IPSec tunnel first, and then make a secured, authenticated, and encrypted connection to the remote host. That is implemented in libreswan, which is a VPN IPSec library for Linux. The IPSec key used here is already specified in an RFC. It's already a rather old RFC from, I think, 2006, 2007. And the IPSec key can either be looked up in a forward zone, or if just an IP address has been given to the application, then that IP address can be looked up in the reverse zone with the same IPSec key. And the last part of DNS was the DNS bounds BOF, another birds of a feather meaning. DBound stands for domain boundaries, and there was a discussion whether it is useful to have a different way to determine the administrative boundaries in DNS. There are certain software products like web browsers and also other software like the DMARC software that is for fighting spam in email, that need knowledge of the domain boundaries in DNS, meaning which part of a domain name belongs to which organization. And today, this is being done by the public suffix list, which is hosted on www.publicsuffix.org. And that is a plain list that lists all the top-level domain and names that are exceptions from the normal rule. Like what we see here is part of the UK namespace. It says that UK and schools UK is part of the top-level domain administrative boundary, but there are some exceptions like britishlibrary.uk, which is a second-level domain, which does not belong to the top-level domain registry, but belongs to, of course, the British Library. And today, this information is being maintained in a just plain list, and discussion was here if it would be better to store that information directly in DNS, because the people who compile the list, they have often to guess where the administrative boundaries are, while the domain owners, they actually know where these boundaries are and could put that into the DNS. However, the BOF session doesn't made any decisions here, so this discussion will continue on the mailing lists. And that was all the DNS. Now I have DHCP, and we have 4 RFCs that have been published since last IETF. First one is a document describing the requirements for the failover protocol. Currently in DHCP v6 we don't have any failover. However, it's possible to just implement multiple DHCP v6 servers in a network to have redundancy, but it would be nice to have the same failover protocol that we have in DHCP v4, and this document describes the requirements. Then there is an RFC describing a radius option for a DHCP v6 relay agent, which is of interest of everyone using radius for authentication in a network. In this, the relay agent can make a sidestep to a radius server, request additional information about the client, and depending on the information from radius, can then give that to the DHCP server, and the DHCP server can then make a more informed decision on what options to deliver back to the client, like what IP address from which subnet, which range, and so on. Then there is now an option to distribute address selection policy using DHCP v6. Quite important because so far address selection policy could only be maintained or administered locally, which doesn't really scale for a large number of hosts, and address selection can now be distributed through DHCP v6. And while DHCP v6 is rolled out now in networks, it was found that the retransmit time for solicitation messages and for informational DHCP requests were too low in the previous DHCP v6 standards. They were 2 minutes before, meaning that a client would ask every 2 minutes for a DHCP v6 server in the network, even if there is no one, which can create a lot of traffic in a large network. And the new RFC permits that these values being made bigger, reducing the DHCP request traffic in large networks. Then there was a best current practice document being presented, which is the DHCP configuration on the basis of network topology document, which describes how DHCP clients, relay agents, and servers interact. That document doesn't specify a new protocol or anything. It just explains best practices on how to deploy DHCP and how DHCP relay agents and DHCP servers work today and are implemented today, and what can be done to customize the DHCP configuration given back by the server based on the location of the clients. The document covers both IPv4 and IPv6, and I would recommend that document for everyone who implements DHCP in a larger environment. Larger means more than a handful of subnets. This is especially interesting for environments where there is a cascaded subnet infrastructure, so where one relay agent is sending information to just another relay agent, and that one goes then to the DHCP server. And quite a big work has been started right now for DHCPv6. The original DHCPv6 RFC is now over 10 years old. It has been published in summer 2003, and the IETF working group is now working on a revision, a new version of that original DHCPv6 document. A reason for that is that we have much more operational experience today with IPv6 and with DHCP and IPv6, and that operational practice needs to be merged back into the document. Also, some parts of the RFC need clarification today, and there were quite a number of RFCs that changed the original document. So for someone who implements DHCPv6 today, that someone needs to read the original document and then the deltas of the changes in all other RFCs. And the aim for the new RFC is to merge all the changes back into one document. There's a bug tracker and a mailing list at these links that we see here, and there's a GitHub repository with a new document. Currently, that GitHub repository is just a copy of the original document, but people start working now on that document, and you can follow all the changes and the progress there. And if you have feedback, or if you ever had questions on DHCPv6, you can contribute. You can ask questions to the people, the group, the working group, and they will be open to take your questions, your change requests, and might consider that for the new version. If you are not, if you don't like to talk to the working group yourself, or you don't want to subscribe to the mailing list, you can also send your input to me, and I will then forward that to the working group and work with them. About failover design, we have seen there's an RFC about the failover design statement, and there was the document that really specifies then the protocol being given to the Internet Engineering Steering Group, the ISGE, in the last IETF meeting, but that document came back and is now split into two documents. There will be one document talking about the failover design, and another one talking about the actual protocol specification. And that what we know as a failover protocol in DHCPv4 is actually a combination of failover protocol plus load balancing. And the load balancing algorithm, which has been implemented in both the IC DHCP server and the Microsoft DHCP server, is now also be standardized for DHCPv6. It's basically the same algorithm where a certain hash is given, and the client identifiers then being used to distribute a lease to one of two DHCP servers. The draft on address registration is quite an important work. This covers the requirements of hosts that generate their own IPv6 addresses, either through auto configuration or cryptographic generated addresses or privacy addresses to be able to send a request for putting their IP address and their host name into DNS to the DHCP server. This is something that has been implemented in the Microsoft world for a long, long time, and meaning that clients can register their names and IP addresses in DNS, but in some environments, the DNS administrators don't want to open dynamic updates for all clients in the network. So in that networks, it might be of use to have a way to tell the DHCP server to make the mapping into DNS. And this draft defines a new DHCP request that a client can send to the DHCP server and ask the DHCP server to put the forward mapping and the reverse mapping into DNS. That way, only the DHCP servers require update permissions on the DNS servers and not all the clients. It also is a way to create a central registry of all the hosts that have self-generated IPv6 addresses. Today, we have quite a number of enterprise networks where the network administrators are hesitant to deploy stateless auto-configuration because there is no central registry where they can look up which host owns which IP address. With this extension, that would be possible again because all the automated generated addresses will then be mapped through the DHCP server into DNS, and that is a central point where the IP address to host lookup can be done. Quite a number of networks nowadays try to minimize IPv4 usage, especially in the backbone and access and data center networks. And these companies would like to have a wide provision IPv4 clients through DHCP-v6, meaning they have their data center, they have their access or backbone networks on v6 only, but they have still IPv4 in all the networks, all the subnet where client machines are in. Instead of having IPv4 for DHCP also in the data centers, they would like to have a way to send IPv4 address configuration information over DHCP-v6. And there's a draft that defines a new option that allows a DHCP client to send a request for an IPv4 address over DHCP-v6. That draft has been implemented as an experimental installation on top of the Bind 10 DHCP server. That was done by Tsinghua University in China. They have used the Bind 10 DHCP server, and they say it was a very minimal change, just a few hundred lines of code being changed, and then they have this functionality being implemented. As a side note, Bind 10, there's a new version coming out just last week, which is the version 1.2.0 beta 1, and we expect the release version being out either in April or May for those who follow the Bind 10 developments. And there's another draft, the draft IETF DHC v4 configuration draft, that discusses the various options available to send IPv4 configuration information over IPv6 only networks. And I think this is the last one on the DHCP part. This talks about authenticate or securing DHCP-v6 messages with a public key infrastructure. This is often required because DHCP-v6 is more powerful than DHCP-v4. For example, both the servers and relay agents can send reconfigure messages to clients and trigger the clients to reconfigure their network stack. And if that is not authenticated, then a malicious intruder could do that, just force all the clients in a certain network to reconfigure, which could do a lot of harm. And this proposal defines a way to secure the communication between both the clients or the client, the relay agent, and the servers using a public-private key pair, basically signing the communication. The keys can either be configured manually, which has a scalability problem, or can make use of the public key infrastructure. And this will be implemented somewhere. This might be also a good opportunity to store then the public keys in DNS using the DANE mechanisms. And that was all about DHCP. And sorry, I'm running a little bit late of time. So I hope you have a little bit more time for the IPv6 part. I'm skipping here the discussion on the RFCs and talk about the stable IPv6 interface identifier. Now, historically, the interface identifier, which is the right-hand part of an IPv6 address, have been created from a MAC address with an algorithm that we see here on the slide. The MAC address is being used, then the value FFFE has been inserted in the middle, the 7th bit, the globally managed flag, has been flipped, and then the prefix has been prepended to it to create a full IPv6 address. Now, using this kind of identifiers, that is, identifiers created from the physical link layer address, has privacy problems. It allows some outsider to correlate the activities of a host over time to see like what websites a client is surfing on, which email servers the client is communicating with, and so on. It also allows the location tracking, because if the client moves between networks, the host identifiers always is the same and identifies the machine. So by comparing the prefixes with the host IDs of an IPv6 address, some outsider could track where a client with an IPv6 address is moving. So from which network to which other network it is moving. It also makes address scanning easier because the link layer addresses are well known. At least the vendor parts are well known, and the FFFE data that is inserted is well known. That leaves just a little part of the identifier random, and that makes it very easy, easier, not very easy, but easier for an attacker to do address scanning in IPv6 networks. And last, because the link layer address also contains the vendor identifier, so we can see whether a device is an Apple device or a Lenovo device or an HP device, that could lead to attackers directly finding device-specific vulnerabilities. Therefore, the IETF is working on a draft that allows to create stable interface identifiers that are not derived from the MAC addresses. It's a way to create unique and stable identifiers, but these are unique for every network. So the identifier is always the same if I'm like in the office network. In the office network, I always have the same identifier, but if I go to the internet cafe outside, then there I get a new interface identifier, which is again stable for that network, but has nothing to do with the identifier that I have in my office network. So that will enhance the privacy. Then there's an informational draft on the question why IPv6 subnets are always /64. That draft doesn't change anything in the protocol in IPv6 at all. It just explains the reasoning behind the choice of /64 networks. It also lists what protocol IPv6 protocol functions will break if a different bit boundary is being chosen, like smaller or larger networks. And it also has a table of operating systems that will break if either a smaller or a larger prefix is being used. Extension headers have been a problem in middle boxes. Now, IPv6 has this notion of extension headers to carry extra information for end hosts or other machines, and these extension headers cannot be parsed by middle boxes very easily, because the size of the extension headers is unknown for a middle box. And that was on purpose in the original IPv6 specification, because the idea in the IETF was that the core of the network should be dumb. The machine, the middle box, the router should just forward package, not inspecting them at all. However, the reality today is that middle boxes often drop traffic because they don't understand extension headers in the header chain. So here we see an example. We have a header chain starting with an IPv6 header and followed by a routing header, and then there is an unknown header in the middle in between, and the size of that is unknown. So a middle box like a firewall or an intrusion detection system has no means to know where the TCP payload is, for example, to inspect the port information, the source and destination port for the TCP payload in there. And instead of not being able to enforce a security policy, then the firewall will drop the package completely. And to solve this problem, a draft is proposing a universal extension header, which has always or has a defined size and has a subtype field that allows for 265 more extension headers in the future. So, because we're running out of time, let me skip over the last ones and let's start with the question and answer section. Paul?
Yes, thank you, Carsten. A lot of the questions that we've received throughout the course of this are actually kind of housekeeping. So I do want to reiterate that everybody will be receiving a link to the recorded webinar, as well as a link to the slide deck. So don't worry about that. So now on to the technical questions. First off, encryption in DNS seems necessary, but it complicates troubleshooting. When can we expect DNS encryption to appear in clients and the server?
That's a hard question, because encryption changes the software. So it would require that a lot of software operating systems and DNS servers being replaced. I expect that the first protocol specifications might be available later this year or beginning of next year. However, how fast these are then implemented in software and deployed would take probably more years. With recent experience, rollout of like DNSSEC and such, I would expect it can easily take 5 or 6 years until we see widespread adoption of encryption in DNS. I hope it will be faster, but we will see. So it will not be there tomorrow or at the end of this year. No way.
Now, how about DHCP v6 address registrations? Are only hosts allowed to send the address registration request, or are also routers or other machines that act as proxy for the registration?
Okay. Yeah, as far as I remember, the draft doesn't really specify that. It's a good question. I probably need to take that question over and to the mailing list and ask for clarification on that. I would, from I would just guess that it would be possible for a proxy like a relay agent or something to also trigger the registration. But yeah, we'll check on that, and we will post the answer if we get one on our webinar page later.
And that was actually a good segue, Carsten, because I do want to repeat Carsten's offer. If anybody does want to communicate via, using Carsten as a proxy to the panel, feel free to email either myself at pterrell or to Carsten. You'll be provided our contact information as well.
Yes. So for those who still are here, I've just skipped a few slides. Do we have more questions, or should I just go over the remaining slides?
Looks like that's the questions for now. So carry on with the slides then, Carsten. Thank you.
Okay. So just a little bit more. There was a large discussion, or there was some discussion on how automatic address configuration and DHCP can interact. And there are a couple of documents being worked on in the IETF. One is the problem statement of having both DHCP and auto configuration in one network. There is a document that with the name Interaction Operational Guidance, which during the discussion has been decided to rename that into Considerations, not Guidance, which talks about using just DHCP-v6 only deployment and using stateless auto configuration only deployments and using mixed deployments, meaning both auto configuration and DHCP-v6 on the same network. And then there is also an implementation guide for people who implement software. For network administrators, probably the interaction operational consideration document is a good read there. In the same direction goes the recommendation for using unique local addresses. Unique local addresses, or ULRs, are the private addresses in IPv6, and there are quite a number of opinions in the IETF whether using ULAs is a good idea or not. There is one camp that says that global addresses should be globally unique addresses, public routable addresses should be used all over the place, and there are other people who say that ULAs have their good points and they should be used. This document explains one of the use cases, or some of the use cases of ULAs, and also possible drawbacks. So anyone who is designing IPv6 networks should have a read on that document. And there's a document on design choices for v6 networks, which answers the question whether it makes sense to mix v4 and v6 traffic on the same link, or whether the traffic should be separated by VLANs or other technical means, and whether routes should be using a link local addresses, only link local addresses, or whether they should point to either ULA or globally routable addresses. And there's also a discussion on the choice of the interior gateway routing protocol, OSPF versus ISIS, so it talks about the strengths of and the weaknesses of both protocols, both in the view of having a mixed networks with both v4 and v6. IPv6 makes extensive use of multicast, link local multicast, which was a good idea at the time when IPv6 was designed back in the 1990s. Since then, we have gotten quite a number of new link layer technologies, such as wireless LAN. And in some link layer technologies, having multicast is actually quite expensive in terms of battery life. And with more and more mobile devices that need to go to sleep to conserve the battery power, using multicast for IPv6 in the link local networks might not be a good idea. So the IETF is currently discussing an option to replace multicast in these networks with alternatives, probably unicast. That does not mean that multicast will go away. It will just define an option so that in specific link layer technologies, multicast can be replaced with something else, which is more or better suited for mobile devices with limited amount of memory in the batteries, energy in the batteries. Okay, that was my overview of the IETF last week. Paul, do we have more questions coming in? Or should we wrap it up?
I think we can wrap it up unless anybody does have any last-minute questions. Again, the presentation will be available online afterward.
And repeating again, we are really interested in your feedback, whether you like the format, whether we have it shorter, less slides, more explanations, more about the published RFCs, more about the drafts, etc., etc. Let us know, and we will hear you. And hope we will see you or hear you again in one of our upcoming webinars.
Excellent. Thank you all for your time, and thank you, Carsten. Again, feel free to email us with any questions.